In the last lectures, we learned how steps and ramps appear in the S-domain as 1 by s and 1 by squared. Now we'll go one level more realistic. Signals that start and stop. Pulses, pulse trains, and sawtooth waveforms. This is where many students feel forced into Fourier series immediately. But the point of this course arc is, you don't need to start with Fourier to reason correctly. In the S-domain, we can decompose these finite signals into combinations of the primitives we already understand: steps, ramps, delays, and resets. The key shift is this: a finite input isn't a single event, it's multiple events. A pulse is not one shape, it is literally two step events, an on event at time 0 and an off event at time t. A pulse train is not a sinusoid like periodic signal, it is repeated on and off events. And the system's memory may not have time to die before the next event. And a sawtooth is not just a ramp, it's a ramp followed by a reset, repeated, which means it stresses low frequency tracking and also injects sharp high frequency events. So the theme of today is structured excitation. The input structure determines how many times you hit the system's modes, when you hit them, and whether those mode responses can overlap. So why do finite inputs need careful treatment? Because they start and stop. That sounds trivial, but in an LTI system, every start or stop is an event that excites modes. If a system has memory, like a capacitor voltage or a current, then the response from one event doesn't vanish instantly. It decays according to the pole time constants. If another event happens before the decay is done, the new response adds to the top of the old one. That is memory overlap. This is exactly what happens in digital electronics when pulses arrive faster than an RC can discharge. It is what happens in PWM converters, where the ripple from one cycle stacks with the next. It's what happened in sample data sensing when the system never truly returns to baseline. A student mistake is to look at a pulse and say, it's like a step but shorter. That misses the central phenomenon: two events separated in time interacting through system memory. So in this lecture, we won't chase waveforms first. We'll chase event timing versus pole decay time. Now we define a finite pulse in the cleanest way possible. A unit pulse of width t is simply defined as a unit step turned on at time t equal to 0 and turned off at time t equal to capital T. That is the entire definition. Now that definition is already telling you the physics. The system gets one excitation at the start and another excitation at the end with opposite sign. The only new ingredient here compared to earlier features in time delay. So in Laplace, delays become exponential factors, that is e power minus st. So when you take the Laplace of the signal, you get 1 minus e power st by s. This is not an approximation. It's exact, and it gives you a powerful viewpoint. A pulse is a step factor multiplied by a finite duration factor, which is 1 minus e power minus st. You can already predict that it has a step-like low-frequency emphasis and also a second event at time capital T. The factor 1 by s is a step-like part. It tells you low frequency or steady behavior is involved. The factor 1 minus e power minus st is the two-event structure. It literally means one event now and another thing after capital T seconds with the opposite sign. So the pulse is not one input, it is a two-step excitation separated by time t. That means you can predict the response using step response reasoning without doing any new path. You don't need Fourier intuition. You don't need to hand wave. The algebra already contains the event decomposition. A common student error is to say pulse response is a scaled step response. No, pulse response is a difference of two step responses, one starting at 0 and one starting at capital T. Now we write the system's response in the S domain. For a pulse, y of s becomes h of s into 1 minus e power minus st by s. And this is where the structural thinking becomes powerful. Rewrite it as h of s by s minus e power minus st h of s by s. Now h of s by s is the S domain expression for the step response. So what does this mean? This means that the pulse response in time is a step response starting at time t minus another step response starting at time capital T. So the pulse response is literally the response is turning the input on minus the response to turning it off after t seconds. Without any inversion, you can already predict modes are excited at pulse start, re-excited with the opposite sign at the end, and the interaction depends on whether the start response had time to die before the end event. This is the key idea you must walk away with. Let's apply that to a second order system with complex poles. A second order system can ring. That ring down is a mode, a decaying sinusoid. So if you apply another pulse, you get one ring down starting at time t equal to 0, and then at time t equal to capital T, you get another ring down starting there but with the negative sign. Now timing matters. If capital T is close to the natural period or half the period, the second ring down can land in phase or out of phase with the first. In phase means it reinforces, and out of phase means it cancels. This is how pulse width can suppress ringing or create dramatic ringing without changing the system at all. Students often blame the waveform shape, but the deeper truth is this is a pole time scale interaction. The pulse is just scheduling the two excitations. So what does the pulse width capital T really control? It controls how much the mode decays between the on event and the off event. If T is very large compared to the dominant time constant, then by the time the off event happens, the on response is already gone. The two events are essentially independent of each other. If T is comparable to the time constant, the off event happens while the response is significant. The subtraction can cancel a lot, or it can create visible ringing depending on the system. Now if capital T is very small, the system barely has time to move before the off event arrives. So the net output may be small, almost like a very tiny tap. This is why pulse width control in electronics or control systems is powerful. It shapes how modes are excited by controlling overlap. Now pulse trains. A pulse train is just a pulse repeated periodically. But that repetition fundamentally changes the behavior compared to a single pulse. Because now you have not just two events, but an infinite sequence of on and off events. If the system is fast, meaning it decays quickly between pulses, then each pulse response is mostly isolated. The output looks like a repeated, clean transient. But if the system is slow, the dominant pole near the origin, then the decay between the pulses is incomplete. The output doesn't return to the baseline. It accumulates. Baseline shifts. Distortion appears. This is the memory overlap phenomenon in its strongest form. This is extremely common in sample systems and switching power electronics. Students who only think in frequency response often miss this because frequency response feels like it should solve periodic circuits. But periodicity does not eliminate transients automatically. This slide is emphasizing something very important. Pulse trains are not merely frequency response problems, they are mode accumulation problems. Each pulse excites the same modes. If the repetition period is short relative to the decay time, then the next pulse hits the system before the previous response has died. The modes accumulate into a steady periodic regime that can have a large DC offset and large ripple. The key parameter is this P, the repetition period relative to tau. A practical rule: after 3 tau, about 95% of the mode has decayed. So if P is less than 3 tau, overlap is strong. If P is much larger than 3 tau, overlap is weak. Students often say, but if it's periodic, so it's steady. The current statement is, it may become steady after transients. But what steady means here is a periodic orbit that can be offset or distorted due to memory. Now we look at an example of a slow pole close to the origin. A slow pole means a long time constant, and a long time constant means memory process. So if you drive such a system with a pulse train, the system never fully relaxes. So the response to each pulse begins from a non-zero initial condition that itself was created by previous pulses. This creates baseline shift and long-term distortion. Even without computing exact waveforms, you can see the cause in the S domain. Poles close to the origin mean slow decay. Short repetition period means repeated excitation. Together, they guarantee accumulation. A student misconception here is to treat each pulse as independent. That's only true when P is much larger relative to tau. Now this slide compares sinusoids and pulse trains. A sinusoid excites one frequency and tends to lead to a steady pattern. Pulse trains, on the other hand, excite many frequencies, but more importantly, they repeatedly excite transients. Frequency response can tell you how harmonics are filtered. Yes, but it does not automatically tell you how quickly transients die relative to the pulse timing. That is an event-based timescale reasoning we are emphasizing more. So don't let the phrase periodic input trick you. Periodic does not mean simple. Sometimes periodic signals are the hardest because they stress both frequency content and time domain memory overlap. Now to the sawtooth. Many people think Fourier series for sawtooth, but here we want a structural decomposition first. A sawtooth is a ramp followed by a reset. The ramp portion stresses low frequency tracking. Can the system follow a steadily increasing command? The reset is a sharp event. It injects high frequency content and can excite high frequency modes. So with sawtooth, two stresses happen quickly. Low frequency stress from the ramp and a high frequency kick from reset. This is a beautiful example of why thinking in S-domain primitives is powerful. You can predict flattening of slopes from limited low frequency gain and ringing at resets from higher modes without doing Fourier yet. Now predict the response. If the system has limited low frequency gain or cannot track the ramp well, the sawtooth output will have a reduced slope and increased lag, meaning the ramps flatten. At the reset, because the input changes suddenly, the system sees a sharp change, which excites faster modes. This can produce ringing or spikes, depending on the pole location and zeros. In real life, sawtooth signals show up in the PWM ripple, in integrator-based circuits, and in DAC waveforms. Engineers often see glitches at reset edges. That is exactly the high-frequency excitation we're talking about. And notice, we predicted all of this from ramp plus reset, plus knowledge of the system poles. No Fourier was needed to forecast the qualitative behavior. So let's confront the misconceptions listed here. Pulse response is just a scaled step response. No, it is step on minus a delayed step off, 2 events. A periodic input always leads to a clean periodic output. Not immediately, and sometimes not clean, even in steady regime. Memory overlap creates baseline offsets and distorted periodic orbits. Sawtooth distortion requires Fourier analysis, not for first-order prediction. Ramp plus reset reasoning predicts the main distortions. Frequency response predicts pulse behavior. Frequency response helps with harmonic filtering, but it does not automatically capture transient overlap timing. You need pole time constants and event scheduling. These misconceptions persist because students focus on waveform shapes instead of event structure and system memory. Now this reflection slide is the central summary and is worth saying slowly. A pulse is not one thing. It is two step events separated by time t. X of s is 1 minus e power minus st by s. So a pulse response is literally two excitations separated by t. Pulse trains repeat those excitations and create overlap when decay is slow. And sawtooth is ramp plus reset. Stresses low frequency behavior, reset stresses high frequency nodes. If you can answer the reflection questions using only algebra and pole time constants, you truly understand the material in an engineer's way, not as memorized shapes. So let's do a full numerical example. So let's take h of s as 1 by s plus 2. So this is a stable first order system with tau equal to half a second. So if the unit is a pulse of width 0.5 seconds, x of t is u of t minus u of t minus 0.5. The key technique is pulse response equals step response minus a delayed step response. So let's compute the step response. For h of s as 1 by s plus 2, the step response is half into 1 minus e power minus 2t u of t. Right? And so therefore the pulse response is going to be given by y step of t minus y step of t minus 0.5. So I'm delaying the response after 0.5 seconds and with the opposite sign. So now for let's do the piecewise result. For t between 0 and 0.5 seconds, you have a rising pulse, and y of t is given by half into 1 minus e power minus 2t. Beyond 0.5 seconds, the subtraction turns on and the output begins to decay. So I have 1 half of 1 minus e power minus 2t minus half of 1 minus e power minus 2 into t minus 0.5. In other words, you get y of t as half of e power minus 2t into e minus 1. So you see that after the pulse ends, the output falls back towards 0 with the system's natural mode. This example makes the core idea concrete. The off event is literally subtracting the delayed step response. Now let's look at the accumulation example. Let's take h of s as 1 by s plus 1, so tau is 1 second. And let's apply a pulse train of magnitude 1, width of 0.2 seconds, and a period of 0.5 seconds. So now because tau is large compared to p, the system cannot decay fully. The result is a raised baseline. We can compute the steady periodic regime using the simple recurrence. So let y0 be the value right when the pulse begins. During the on interval, with input 1, the system moves forward towards 1 with an exponential approach. During the off interval, that is from W to P, the input is removed, so the system decays with a response e power minus P minus W. And the steady periodic condition is y of P is back to y0. So you can compute the factors and you get y0 as 0.3413 and y1 to be 0.4607. So what you see here is that the output never returns to 0. It oscillates between 0.341 and 0.461. So here, even though x of t returns to 0 every time, y of t does not return to 0, right? And the baseline is shifted. The DC content of the signal increases, right? And this is where the system memory takes over, right? That's causing this difference between the Ymin and the Ymax, right? And that's because of the incomplete delay. So this is what happens in RC smoothing in the PWM. You see the DC offset and ripple and wonder where it comes from. It comes because there's incomplete decay between repeated events. Now let's look at the same sawtooth through this first order system. So consider one period with p equal to 1 second and a sawtooth that ramps from 0 to 1 and then resets. So if you solve y prime plus y is equal to t with y of 0 is equal to 0, we get y of t and y of t plus 1. So you see here that t equal to 1, the input jumps back to 0. So the ramp demands low frequency tracking and the output slope is reduced and lags. Reset is a sharp event, excites the fast transient mode of e power minus t. So when you compute it, when you solve the differential equation, you get the solution of y of t as t minus 1 plus e power minus t. And that t equal to 1 minus y of 1 is 0.3679. So even though the input reaches 1, the output is reaching only 0.368. So there is a flattening or lag at the output, right? This is what I said when I meant that the output is not able to follow the input faithfully. It is flattening. So while the input rises from 0 to 1, the output is only rising till 0.368.